All right, folks, this is the last video on special cases of rational functions, or this particular kind of special case. We're actually going to do another special case for Thursday's class, or for day 2. When we see this, we want to try and understand, based on the last video, is there a hole at positive 2, or is there a vertical asymptote at positive 2? So if you remember from the last video, the way we answer that question is by doing synthetic division. We take the 0 of the denominator, the root of the denominator, and the root of x minus 2 is positive 2. So we'll put that in the half box. Then we're going to do the synthetic division on the numerator. So we're going to put a 1, then a negative 6, then a negative 13, then a positive 42. And if we get a remainder of 0, we know that it is a whole. If it is a whole, we can then cancel x minus 2 and then graph whatever is left over. So we'll put a 0 here. 1 plus 0 is 1. 1 times 2 is 2. Minus 6 is negative 4. Times 2 is negative 8. Plus negative 13 is negative 21. Times 2 is negative 42. And 42 minus 42 is 0. Now, because we have a remainder of 0, we know that x minus 2 is a factor of the numerator. So the numerator can actually be factored into x minus 2 times whatever is left over here. If this is an x to the third, this becomes an x to the second. So we have x to the second, x to the first, and a constant. Okay, so we have x squared minus 4x minus 21, all right, over x minus 2. So we have factored the numerator. So now we can cancel the x minus 2, and what we have now is f of x is equal to x squared minus 4x minus 21, where x cannot equal 2. So we're just not allowed to plug 2 into it. Now, if we did plug 2 into it, that would tell us where the hole is, the y value of the hole, right? So we're going to go ahead and plug 2 in. 2 squared minus 4 times 2 minus 21. 2 squared is 4 minus 8, so 4 minus 8 minus 21 is equal to, let's see, negative 33. Negative 33. So there's a hole at 2 and negative 33. All right? Now, if we wanted to graph this, it could be very difficult because we have 2, 1, 2, and then negative 33 is way down here. So what I'm going to do is just way down here, I'm going to put a circle indicating a hole, and I'm going to put 2, comma, negative 33. And we know that that hole is at 2 and negative 33. Now, here's something interesting. Now we know where the hole is. But we would like to graph this quadratic, okay? And we know that this is, if you look at this, this is factorable. This actually factors into x minus 7 times x plus 3, all right? And so if we wanted to graph the quadratic, these two factors, they indicate the x-intercepts. They're the roots of this polynomial, where y is equal to 0, where the function is equal to 0. So the root here is x equals 7, and the root here is x equals negative 3. So we're going to put an x-intercept at 7, 1, 2, 3, 4, 5, 6, 7, right there, and at negative 3, 1, 2, 3. Okay? Also, we can identify where the axis of symmetry is by doing negative b over 2a. Remember, in a quadratic, the first number, that's an a. The second number, the coefficient of the x is b, and the constant is c. And if we do negative b, so that's negative 4 over 2 times a, over 2 times 1, negative 4, or negative 4 is 4, 2 times 1 is 2, 4 over 2 is 2. So at x equals 2, we have the axis of symmetry. 1, 2, okay? We have the axis of symmetry. Oh, that's interesting. That means, wow, you know what happened? It's going to go right through the hole. And you know what? The only part of a quadratic that is at the hole is the vertex. That means that the hole in this function is actually at the vertex. Because if we plug this in, when we plug the x value of the axis of symmetry into the function, we get the y value for the vertex. And we've already plugged 2 in. We got -33. So we know that the vertex of the function, that hole is actually at the vertex of the function. And so now that we have the axis of symmetry, we have the vertex, we have the x-intercepts, now we need the y-intercept. Well, the y-intercept is the c value, -21. That's somewhere down here. I don't know perfectly where. And now we can draw a curve, a parabola, through these points, and we have a rough sketch of this function. And it's not just this function, it's this function. That's a rough sketch of this function. It's a special case of a rational function that actually looks like a quadratic. It looks like a parabola, okay? And that's important to understand. We're going to do one more example of this, and then I think that's it for this section. Okay, so I've got this rational function here, and we want to graph it, and we want to determine first, does it have a vertical asymptote, or does it have a hole? And the way we would do that is with synthetic division. If it has a hole, then we can factor the numerator and then cross out the x minus 5 factor, and then we can graph whatever's left over. Okay, so let's do synthetic division with the root of the denominator in the half box. The root of the denominator is 5. So we put 5 in the half box. 5 is 40. -40 plus 40 is 0. So we have a remainder of 0. That means that the numerator can be factored, and x minus 5 is one of the factors. So this is going to become x minus 5 in the numerator, and then what's left over here is this is x to the third, that makes this x to the second, that makes this x, and that makes this a constant. So 1x squared is just x squared, minus 6x, and then plus 8, all over x minus 5. And so now we can cancel out the x minus 5's, and all we have left is f of x is equal to x squared minus 6x plus 8, where x cannot equal 5. We are not allowed to plug 5 in. However, there is a hole when x is equal to 5, and we can find out the location of that hole by plugging 5 into this function. We have 5 squared minus 6 times 5 plus 8. This is 25 minus 30 plus 8. 25 minus 30, that's negative 5. Negative 5 plus 8, that's positive 3. Okay? So we know that there is a hole at 5 and positive 3. Okay? So we're going to go to 5 and 3. 1, 2, 3, 4, 5. 1, 2, 3, and we're going to put a hole there. Okay? Now, this function, f of x, x squared minus 6x plus 8, that is factorable. And if we factor this, it becomes x minus 2 times x minus 4. And so the roots of x minus 2 and x minus 4 are x equals 2 and x equals 4. And so the roots of the individual factors are also the roots of the function itself. So this quadratic has roots or zeros, x-intercepts at x equals 2, 1, 2, x-intercept, and x equals 4, 3, 4, x equals 4. So the graph is going to pass through both of these points. Now, we got to find the vertex, because this is a quadratic, so it's a parabola. It's either an upward turning or a downward turning. We know this one is an upward turning because it's a positive x squared, not a negative x squared. All right, so the vertex, the x value of the vertex is at negative b over 2a. Well, in this case, b is negative 6, a is 1, and then c is positive 8. Okay? So negative b is negative 6, so that's negative 6 over 2 times 1. And negative 6 is positive 6 over 2 times 1 is 2, and 6 over 2 is 3. So the axis of symmetry, the x value of the vertex, is at x equals 3. Now, this is not an asymptote. I'm not drawing a dashed line as an asymptote. I'm actually drawing a dashed line as the axis of symmetry. If you go back to your 10th grade math or whatever, when you learned about parabolas, we would often represent the axis of symmetry on a parabola by a dashed line. But I'll take it out if it bothers you. Okay, but let me leave it there just for a minute. And so, when x is equal to 3, we got to plug that into the original function. 3 squared is 9, minus 6 times 3, that's 18, plus 8. 9 minus 18, that's negative 9. Plus 8 is negative 1. So we know the vertex is at x equals, so the vertex of the parabola is at x equals 3 and y equals negative 1. All right, get rid of this stuff. I'll also get rid of the axis of symmetry if it bothers you, if you think it's a vertical asymptote. So 3, negative 1. 1, 2, 3, negative 1 is right here. So that's the vertex of this parabola. The y-intercept is always the c value. So the y-intercept is positive 8. 1, 2, 3, 4, 5, 6, 7, 8. That's right here. And since the axis of symmetry has a reflection on the left and the right, the y-intercept is 3 units to the left of the axis of symmetry. So I'm going to go 3 units to the right. Okay, so we've just plotted the roots, the x-intercepts at 2 and 4, the vertex at 3 and negative 1, the y-intercept at 8, at positive 8, 0, 8. And then we know that across the axis of symmetry, there's going to be another point that's on the same line at 8 as the y-intercept. The y-intercept is 3 units to the left. We're going to go 3 units to the right and plot another point, because we know that parabolas have a symmetrical shape. They're equal from the axis of symmetry on both sides. And so now we can graph this, and we're going to go through the hole. We're going to be flat kind of down here. Then we're going to go through here. Then we're going to go up through the y-intercept, then through this 0, then through this hole, and then through that point. And it's really rough, but that is the graph of this rational function. Okay? And so this is the last special case we're going to look at today. And what it is that I'm trying to show you is that sometimes rational functions, if you cancel the denominator as a whole, you can actually wind up having a function that looks like a function that is not a rational function, but it will always have a hole in it somewhere. Okay? That's all I have for you.